Good afternoon to everyone in the room who has braved this terrible weather, and I'm sure we'll have people arriving in drips and drabs with the weather. And thank you for everyone who is online and tuning in online. We're gathering this week in preparation for the 11th Non-Proliferation Treaty Review Conference, and as our colleagues discuss the NPT's 3 pillars at the preparatory committee meeting next door at the IAEA, or the Vienna International Center. This week is an opportune moment for us to discuss the critical 3rd pillar of the NPT, peaceful uses. So while peaceful uses offer a variety of ways to contribute to sustainable development, access to them has to be widened. And particularly for developing countries who stand to gain the most from these various applications. So today we will discuss the contribution that coordinated research projects make to expanding access to ionizing radiation and its applications, as well as the importance of raising awareness on how these projects and radiation contribute to achieving the Sustainable Development Goals. So the first, we have a fantastic panel here, and we're going to start with Celina Horak, who is the head of the Radiochemistry and Radiation Technology section at the Department of Nuclear Applications at the IAEA. And she has more than 30 years' experience on the field of radiation protection for healthcare, food and agriculture, environment and industrial applications. Before joining the IAEA in August 2019, she was the manager of the Radiation Science and Technology Center in CNEA, Argentina, and professor in Nuclear Engineering Program and Nuclear Applications Specialization at the San Martin University. Celina, over to you.
Thank you very much.
Sorry, I've forgotten one thing. So anyone who wants to, if you're signing in online, you can pose questions in the question and answer section, Q&A, and it will be monitored, and at the end of the presentations, we will take those questions and answers and from the people in the room as well. And if you're on YouTube, send your questions to VCDNP info events at vcdnp.org. Thank you. Celina.
Thank you very much. Can you hear me well? I put it in the side just to see what what is going on there. So thank you very much, Ingrid, for this invitation. I'm very glad to be here and also share what, from the IAEA perspective, we are doing on this peaceful use of the nuclear application. So I will go from the overview, what the CRP, this Coordinated Research Project activity, are happening in the agency, and going into some details, examples of what we are ongoing now working on. So what the coordinated research activity are doing, what we are working on. The idea of our slogan from our nuclear application contract section administration is uniting the world through research, and of course through the peaceful use of nuclear application. So from their perspective, they are trying to promote or coordinate all the activity that within not only nuclear application department, where I'm working with, is also in the nuclear energy and the nuclear safety aspect. So there are research coordination projects working within this cross-cutting activity, these cross-cutting departments. Also, the idea is to disseminate all the reports and database that are being developed through this CRP activity, additionally to all the scientific and technical publication. Also providing opportunity to scientists from developing countries, plus also with the big experience that we can have from developed countries as well. So all together can sit in the table to discuss and exchange the knowledge and experience. And of course, these proven techniques that are being developed through this CRP can be then transferred to the industry. And there is some program in IAEA, like the TC, the Technical Cooperation Project, that can help in these transitions, no, from the R&D to the industry, how to transfer the technology into them. And this is how this line is showing, no, from the background information that is the demand from member states going to the R&D in different level, because you can go from the fundamental to the application, and finally, through the technical cooperation program, go into the real application of the technology that has been developed through this process. So going more in detail in this timeline that I had mentioned is where this CRP came up. No? They are coming from the demands from member states that are being mentioned through consultant meeting or during some even conference. Any time that we can collect this information from the demands from the member state is how we are putting together in the table to design which is the best activity that we can implement in order to support member states. So sometimes are, as I said, demands from member states from different perspectives, but also there are some individual research in the lab that are showing the trends, that there are some gaps that has to be filled. And this is the background information and why we are launching this kind of CRP. And this is what all these steps are similar, no? We are going to the background information, showing the demands, then implement the coordinated research project that could be from the fundamental to test it at the lab scale, that this technology can really support and provide some solution to some particular topics. But also we can go into another R&D stage, that is when we are starting implementing in the bigger scale, no? Make it more, well, the technology validated. No? The idea is to not just stay at the lab, also going into a bigger scale to show the industry that this can help, really help. And here is where the technical cooperation program can take place and also support, especially at the national level, those institutions that can have validated technology and then can go into more bigger demonstration scale. And also, of course, start interacting with the industry to transfer the technology. What I have put it below is the same strategy that the TRL approach has. The TRL is the technology readiness level approach, is a strategy that has been developed by NASA several years ago, and the idea is how to measure or how to understand the progress of the technology. And it goes from the basic technology into of course, this is the TRL approach is going forward, no? But our program is covered at least up to TRL 7. That is equivalent to develop the pilot plan and the scale-up of the technology. This is how IAEA can support member states, up to them. Of course, there are some extra information that can be delivered after that, but this is the main focus we can support all member states. So now, related to, there is a title that has been done, the CRA, the Coordinated Research Activity, no, in a glance. What is happening in 2023, no? We are covering different, in IAEA, we are covering different areas of application in nuclear energy, in water and environment, food and agriculture, radiation technology, that is like a cross-cutting activity that covers all the other field of activity, health and nutrition, and radiation safety. There are CRP, Coordinated Research Area projects in all these areas. And, well, here there are some statistics on how it's happening now. No? There are many CRP ongoing, and there are a lot of participation from all worldwide, all member states, from developing and developed country. And, of course, there are some funding information there as well. So you will have this statistic on what is the screenshot of the moments by now. And which are the composition of this CRP considering the different area. In the purple color, you can see that the nuclear application is one of the bigger areas in which research coordination projects are being submitted, are being required by member states. Of course, there are others on nuclear energy and nuclear safety, but the bigger component is mostly related to nuclear techniques on nuclear application, in the peaceful use of nuclear application. And now going more in detail among this nuclear application, I'm going to refer particularly to the radiation technology area. Yes, there are, sorry that it has been, yes, the style has been changed a little bit, but just wanted to show that in this year, what is happening in the different area among the radiation technologies area. We are working with different CRP on cultural heritage, in the environment, in health, in food and agriculture, and industrial and material science. These are the main area under which we have already some CRP, and we are going to refer in, not myself, and also our expert here, showing the successful story of that. In the area of health, briefly, we are talking about sterilization of healthcare products, the contamination of raw material, medical devices, packaging material, tissue allograft, blood components, but also advanced biomaterial, those that are going to be in contact with tissue or blood. So all these health applications can benefit from radiation technology. And that is why that there are a very nice commercial application of the health, the sterilization of healthcare products. For example, 50% of the medical devices around the world are sterilized by radiation technology. So this is not something new. But there are still some gaps that we can fill. And that's why we have 3 CRP ongoing. One on enhancing beneficial effects on radiation processing in nanotechnology. It was such a success CRP that now we are having one publication on that. It's under development, it's under preparation, this publication, because of the finding through this CRP at such a good quality that the contest, we're considering that it's really important to have this publication using all this information that has been developed through this CRP. The second one is the radiation effects in polymer material commonly used in medical devices, and this is also to show the different technology, gamma, X-ray, and E-beam, electron beam accelerator, how easily is to go from one technology to another, if there is any difference on that, and the feasibility of implementing this technology. And the third one is one CRP that is upcoming, next year will start, on biomaterial for sustainable health care. Because still there are some biomaterial that can benefit from radiation technology, and especially thinking about some sensor, biosensor. So there are still a lot of room to develop new products. And that is why we're considering this came from the different expert consultant meeting and from our demands from member states. And that's why we're considering that this will be a good CRP to continue working on. On food application, we work together with the Nuclear Application Food and Agriculture Division, and you will see radiation for sanitary purposes, phytosanitary treatment, sterile insect techniques, surface disinfection, mutation breeding. In light blue is the one that we are working together with them, and these are the 4 CRP ongoing. The last 2 are, we have a joint collaboration with the Nuclear Application Food and Agriculture Division. We work together to develop the best strategy for this kind of application. I'm going a little bit faster because I'm taking too much time. And the third one is industrial application of material science. This is another big area that, again, is quite well implemented in many of these applications, but there is some room yet to continue developing. So, for example, we will have in October the last CRP of this development of graph membrane for clean and sustainable energy, and we have had a very nice result from this CRP as well for the developing of membrane that has some functional properties, such as, for example, for producing some catalyst no? For biodiesel, or for membrane for separation of carbon dioxide through methanes, especially for biogas production. And the third one is for energy storage, for fuel cells. So we are developing different membrane with dedicated property. So it has a very, very successful result from different countries. And the second one is the one CRP that recently has been launched on strengthening the use of biomass for synthesis of bioplastic and other compounds. So we know that in the plastic value chain, one of the main sources for using, that is being used for the production of plastic, is the petrol-based sources. So the idea is to replace the petrol-based sources from biomass. Yes, from natural polymer that are not being used. So try to use it and put it in the value chain in order to produce some bioplastic, but also some other kind of compounds. And the preservation of cultural heritage, that, well, we can work on the disinfectation of this cultural heritage and also some consolidation of porous materials such as wooden artifact that can be consolidated by some impregnation with resins and irradiated to make it more strength. And there is one recently launched CRP. The first research coordination meeting was in Egypt this year. So, but this is the second CRP of one ongoing successful CRP. So that's why this is just more advanced, and we will have one expert that will expand on that. So that's why I will stop by there. And then on environmental application, we can treat flue gas, industrial wastewater, sludge, and also upcycling the plastic waste. We talk about the use of biomass to replace the petrol base, but now we can also use radiation technology for upcycling purposes to put in value this plastic waste that is being mismanaged or is being landfill. The idea is to, those that are not really easy to recycle, we can't, with radiation technology, produce some more valuable product. And that's the main purpose of this a new CRP that, well, not new because we are already 1.5 years in progress. That is the last one, recycling of polymer waste for structural and non-structural material. And there are more than 20 countries that are participating in this topic, and it's very, very successful result we are having. But then we have another 2 CRP on radiation inactivation of biohazard using high-power electron beam accelerator and the removal of emerging organic pollutant in the waste by radiation. And this will be also, we have another expert here that will talk about that. So this is just to show how we are coordinating all this activity. This is just, don't have to go into the detail of this small letter, but just to show this is the plan activity, how we are coordinating all this activity in order to see the synergy that can happen among them. So this is our plan, our planning activity, our game. And of course, sometimes we need support because in the IAEA, in this particular field, we don't have laboratories. So that's why we connect with what we call collaborating centers. They work together with us to make science works. No? Of course, we work with the different researchers around the world, but with this collaborating center, we can enhance what can be done, especially when we have some doubts of this can happen or no, or maybe we can, when we need to train some fellow or provide some expert mission, we work together. And in all these fields, we have different collaborating centers. And we have one representative of our collaborating center here that is Suresh, that is going to talk later on. So again, we have with our collaborating centers also a good plan in order to see, especially the validity period of each of them, but how we can synergize the activity among us. And with this, I guess that, well, just to summarize my presentation, we were talking about that I would like to introduce what IAEA is doing in this R&D field for the peaceful use of nuclear activity. I was talking about the promoting and coordination, the cooperative research, and I guess that we connect academia, the scientific organization, the industry through this CRP, and this is what makes sustainable the R&D that is being produced. It makes sense that this can be applied later on. On the dissemination and information through the report and database, well, we prepare, elaborate database with the input from all member states, and also we can generate a lot of knowledge through the CRP reports, guidance documents, international conference, we are working on that. In the case of providing opportunity to scientists in developing countries with CRP, we're considering that it's one of the best platforms to exchange all the knowledge and experience from the developing and developed countries. So all are together in the table and they can discuss and exchange knowledge from each other. And related to the last point, proving techniques, testing and ready to be transferred, well, as you have seen in this timeline, no, the CRP and indeed leading in piloting from the R&D to the piloting prototype. So we are covering all the different steps to implement the technology in the best way. And this is our main goal, no? To not just stay at the lab. This is very important, and the publication and the scientific evidence has to be taken into account. But we have to go forward. We have to scale up the technology and be able that this good science can be transferred to the industry. And with this, thank you very much.
Thank you so much, Celina. Thanks for illustrating the IAEA support to member states through the CRP. I mean, for me, it's just so inspiring that you have a process that is not only expanding the areas of the applications of radiation, but also improving these applications, and then to disseminate these benefits to member states through the technical cooperation program, and to actually have them reach and be implemented by industry and in countries sustainably. And so we're going to listen to Jeremiah, we're just going to call you Jamie, quite frankly. Jamie from the Philippines, on exactly how our first panelist on how this works and what she is doing in the Philippines.
So, good afternoon, everyone. Thank you again for the opportunity to speak to you today. I am Bean Jeremiah Barba from the Philippine Nuclear Research Institute, and I will be presenting on the CRP, particularly on recycling of polymeric waste for structural and non-structural materials by using ionizing radiation, from ideas to execution. So I will be discussing a bit about the motivation behind the CRP, its connection to the New Tech Plastics Initiative of IAEA, an overview of the member states' activities, as well as a case study featuring the technologies done, or activities rather, in the Philippines. So let me prefix this with our shared global problem, which is plastic pollution. While no one can deny the usefulness and versatility of polymers in everyday commodities and in industry, their steadily increasing use and disposal has led to their increasingly proportion in our landfills and leaking into our oceans. This is because for the past several years, the plastic industry has been linear, meaning they produce, we use, and they dispose. And because plastics, as they are now, are not designed to decompose very easily, they tend to accumulate in our oceans and cause a great deal of human health risk and environmental impacts. And so we seek technological interventions that can mitigate plastic pollution. And various recycling strategies are usually employed as an approach to mitigate this pollution as plastics reach their end of life. This can be something as simple as reusing the plastics. There is also what is known as mechanical recycling. Basically, you take the polymer waste and reprocess it back to their original purpose or towards another application. There is also chemical recycling, which is to break down the plastics back to their original components, the monomers, or towards other low molecular weight fragments that are also valuable in industry. And then there is thermal treatment, which is essentially energy recovery from the waste. Now, these conventional processes, however, are still lacking in terms of technological efficiency, economic feasibility, as well as environment friendliness. And that is where nuclear technology can assist as a support mechanism to existing recycling infrastructure. In particular, we have radiation processing, which has been discussed earlier by Celina, to have numerous applications. As we know, ionizing radiation has the capability to alter and modify the structure and properties of materials in various forms and states with little to no additional chemical reactants and at moderate condition, making it environment friendly. In industry, radiation processing has been used for the synthesis and modification of polymers. And this is essentially what plastic waste are. It's still the same material. So the idea is to use radiation processing to also assist in the recycling of these same materials post-use. Now, the mechanisms used in industry like cross-linking, oxidation, grafting, and scission or degradation can also be used towards recycling. Cross-linking and oxidation can assist in the mechanical recycling of polymer waste. Grafting can add value to existing polymer waste by using them as substrate in material valuation. And then we have degradation and scission, which is essentially the theme of chemical recycling. So these same mechanisms can be used in plastic recycling. And this potential is recognized by the IAEA in their initiative for the nuclear technology for controlling plastic pollution, or NUTEC plastics. And one of the components is indeed to use this radiation processing technology to extend the recyclability of plastic waste, especially those that are not easily recycled by conventional processes. And this has been implemented through various technical cooperation projects by various training courses to capacitate each member state and to disseminate information. And another avenue, as discussed earlier, is through the coordinated research projects. So this particular CRP, again, on the recycling of polymer waste for structural and non-structural materials using ionizing radiation, tackles the applied research and development, demonstration, and scaling up feasibility studies to optimize this type of technology in the framework of plastic recycling. Specifically, the CRP aims to develop processes, techniques, and protocols through a collaborative effort on optimizing the radiation processes and then validating the key factors that will ensure that this can be transferred into the end users, the technology adapters. Now, a total of 22 countries are participating in the CRP across Asia, Europe, Africa, and Latin America, and we had a chance to come together during the first RCM just last March 2022. Now, coming from all around the world, each participant has distinct cases dependent on their country's situation, needs, and priorities. So each country can have wildly different polymer waste types and sources. They can have different target industries, different available resources, and different strategies in implementing this kind of project. However, as the participants discuss their proposals and researches, emerging similarities between member states in one of these components ensure that we have an opportunity for close discussion and collaboration so that the project can be implemented more effectively. So going back here again to the different radiation mechanisms that can be used in plastic recycling, there are 3 trends that have emerged between the member states. One is the use of cross-linking for the reprocessing of plastic waste for reuse, or towards high-value products. And this includes the recycling of cable wires, tires, and e-waste. And remember that ionizing radiation is also used in the manufacture of these types of products. So the infrastructure is already there. It will just serve a different purpose. And then for the other countries, they are also focusing on the degradation of polymers, especially single-use plastics, for the production of low molecular weight fragments like fuel, hydrogen gas, and other industrially valuable chemicals. And lastly, the use of oxidation and grafting for compatibilization are considered especially for complex and mixed plastics, which is essentially what can be found in our municipal landfills. They're mixed together, they're not sorted. They are not typically recyclable to conventional means. And by using these types of compatibilization techniques, we can repurpose this plastic waste into upcycled materials and other highly valuable functional materials and composites. Building further on group dynamics, further cooperation is secured through a commitment of resource sharing, be it in technical expertise, the use of irradiators, analytical and processing equipment between member states. So this is very essential since not everyone has equal access to available resources that we have. And lastly, as diverse as the research topics between the participants are, the CRP also recognizes the benefits of a harmonized research approach. So Celina already showed you earlier the technology readiness levels approach to the development of products and technologies. So basically, you break down the project into milestones so that you can easily monitor how it goes from the laboratory to the end users, to the people who are going to use it. And here, for the CRP TRL 3 and 4, which is the R&D component, it is hinged on the basic tenets of pre-characterization of the polymer waste, the study on the effects of radiation, and the validation of the functional test and structural test of these products, which you will remember is part of the objectives of the CRP. Okay, so in the next few slides, let me share the CRP implementation in the context of my country, the Philippines, which focuses on the recycling of post-consumer plastics for the development of high-performance products, mostly for construction applications. And this project is a collaboration between two national agencies, PNRI and the Industrial Technology Development Institute, or ITDI. We have also a private company collaborator, the Envirotech Waste Recycling, Inc., as well as support from our colleagues from the National Institutes for Quantum Science and Technology in Japan. So in the Philippines, a study showed that among the 1.1 million tons of packaging plastics produced in 2019, only 28% is recycled. And this 28% is just PET bottles. So PET bottles is one of the plastics that are more easily recycled through conventional means. Now, the rest of those plastics ends up in landfills. And this means grave environmental implication for this much waste. And also, around 790 million USD of potential market value is lost to the Philippine economy every year. To unlock this material value, there is a need for an intervention technology that can improve the base thermomechanical properties of plastic waste to enable their upcycling into useful high-value products. And here we have proposed what is called as the post-radiation reactive extrusion, or PREX, a process wherein we irradiate plastic waste in order to form radicals and reactive species that can make the material more processable, more miscible, and stronger once they react during the thermal extrusion phase. So you combine essentially what is a radiation intervention and a conventional processing technique. So it is meant to support local recycling capability without needing an overhaul in existing recycling infrastructures. So we were fortunate enough to have strong industry support from the Envirotech Waste Recycling Inc. They are a Philippine-based recycling company which aims to divert plastic waste, especially single-use packaging waste, into useful commodities. And their end goal is to make sustainable housing made from 85% recycled content. And this is a picture of their recycling process. And while this process works for making simple things like school chairs or park benches, it has limited quality when compared against construction standards. So this is where nuclear technology plays a role so that we may improve the property of their products for use in construction application. Now, just to give some highlights on the data so far to support the proof of concept, TRL3, we start with the base mechanical properties of mixed municipal waste. So this is made up of different plastic types from packaging. We have HDPE, PP, LDPE, as well as multi-layer packaging from like candy wrappers or potato chips. So using the PREX process, we are able to make the plastics stronger and slightly more rigid with a 15% increase in flexural strength at a certain dose. And then, introducing natural fiber reinforcement, again compatibilized with the system using radiation processing, we see a 25 to 37% increase in flexural strength with additional flexibility. So ultimately, a positive effect can be seen by optimizing the radiation processing parameters. But of course, these are just initial results. There is still a long way to go to elucidate exactly what radiation does to each component of the plastic waste in order to make sure that the concept is reproducible and sustainable. But again, so far, it looks optimistic, and our industry partner remains committed in working with us into further refining this process. Now, another important aspect that has aided the project, especially in securing additional support, is the financial feasibility evaluation. And thankfully, we have a useful tool in the form of the Excel-based Economic Assessment Method, or EB, crafted during one of the workshops under New Tech, which can calculate the capital investments needed in order to set up recycling facilities using electron beam irradiation, as well as calculate some financial markers in order to assess whether the strategy being employed by the different member states is financially feasible. For our particular project, in the initial assessment, we forecast a benefit to cost ratio of 1.67. So this means that 1.67 economic benefit for every €1 invested is expected from the project. And we hope to increase this value as we further refine our process. Now, summing up the potential benefits of the project so far, we have technical benefits of around 15 to 40% increase in mechanical properties, an economic benefit of 1.67 per euro cost, and of course, the ecological benefits of plastic waste diversion. And armed with these results, we were able to successfully secure additional local funding from the national government to fund resources needed to make our way towards TRL 4, 5, and onwards. And we were also able to present some of these project highlights in the ADB Innovation Fair last October 2022 and the Philippine Chemistry Congress held just last month. So it is important to highlight here the benefit of the CRP in funding basic research, enabling expert access, and coordinating a global collaborative effort among great minds in the field to come up with solutions that extend beyond the confines of a laboratory. The next step now for us is to continue validating our experiments and to proceed with the project towards the adoption of the industry. Now, there are still many steps to take, but the importance of small steps is that together they get a lot covered. and we just need to keep moving forward to achieve the impact we hope for. So thank you very much for your kind attention.
Thank you, Jamie. I think that last slide, everything you said is quotable. So, and I didn't introduce Jamie properly, and I think what's very important to know is, apart from the fact that she is a science research specialist from the chemistry research section of DOST in the Philippine Nuclear Research Institute, is that her past work has led her to develop hemostatic materials for cross-linked polysaccharides. No idea what that is, but it is capable of accelerating hemorrhage control in traumatic injuries, which is amazing, right? And perhaps one day we'll hear more from you about that. But, and she also won a LICA award during the National Inventions Contest and Exhibits held in 2022. So thank you so much for that. And now we'll move on to Professor Pablo Vasquez. And Professor Vasquez is a researcher at the Nuclear and Energy Research Institute, IPEN, and professor at the University of Sao Paulo's Institute inside the Nuclear Technology Graduation Program. He leads a team working on the research and applications of the ionizing radiation for characterization and preservation of cultural heritage artifacts and sterilization of several materials. He has produced many publications, including on radiation process applications, industrial dosimetry, quality control, and development of irradiation facilities. And one of these papers was on the emergency applications of radiation processing for decontamination of personal protective equipment in the COVID-19 pandemic, and on Brazil's experience, which if anyone is interested to read that after this presentation, because we will all be so knowledgeable, we'll be able to read these complicated papers. And he's also participated actively as a lecturer and consultant for national, regional, and interregional IAEA projects. Today he's going to share his work on the CRP development and implementation of cultural heritage, preservation using ionizing radiation technology. Thanks.
Hello, everybody. Thank you very much for the introduction. Before to talk about the CRP project, I want to talk about where is my institute, because I'm so far from here. We are located at the south from Brazil, the name the city is Sao Paulo. We are inside the University of Sao Paulo. We are a special institute with nuclear application. We have almost 11 research centers, and IPEN is working together with the University of Sao Paulo. This is very important to make possible this objective of these research projects, because we are working together with the people, not only with the scientific applications, but with the social applications, libraries, and museums, and this was a key factor, in my opinion, that my institute is inside the university working together. Then, what is radiation or irradiation? This is always, we listen about this, but we live in a world with irradiated products, talking about the food you eat every day. A lot of food was irradiated, but actually this is not noticed in all of the products. However, this technology, the idea is to make an exposition of material of electromagnetic waves. And these electromagnetic waves can get provided by a radio isotope like cobalt-60, for example, and we call this gamma ray, or like a machine, electronic machine, like X-ray, medical X-ray, but a little more powerful. And the name is electron beam accelerators or X-ray. However, the idea of this process is to get three effects: physical effects, chemical effects, or biological effects. To preserve cultural heritage, we are interested in the last related to chemical and biological. Biological because radiation, ionizing radiation in this level can have a biocidal action. We can eliminate with very high quality insects, microorganisms, and bacteria, fungi, even the problem with virus. And by the other side, we can get polymerizations or cross-linking or changing the state of the different kind of polymers. Then ionizing radiation can support this field of preservation of cultural heritage. I'm talking about tangible cultural heritage. It means more like organic materials, like paper, like wooden sculptures, these kind of organic systems, doing first thing, disinfection. Disinfection, we can eliminate all kinds of insects. Insects in different stages of life, like eggs and adult insects, even microorganisms like fungi, in different kinds of materials will not affect the materials. We cannot change the color, we cannot change the condition of the wooden or of the old books, for example. And the second thing, you can do consolidation. When a sculpture, for example, wooden sculpture, is very old and attacked by insects, this creates a lot of holes, they become porous and very fragile object. The idea is to put inside, in the beginning, a liquid, and using radiation to change the state of this liquid to solid, and create, again, a new life to this kind of sculpture, but using ionizing radiation with not chemical compounds. The idea is to avoid this chemical contamination to the world. And this last thing is trying to develop a new nanostructural materials to cleaning cultural heritage. Now, we are doing this last years, is like a hydrogel. You can apply directly on a painting like that, or a paper with problem, and you can remove all impurities or all contamination changing of the surface of these materials. Then, the background of this project was the development, the CRP, of course, was working between 2015 and 2021. It's a project to develop radiation treatment methodologies and new resin formulations to preserve archived materials and cultural heritage. By this time, we need to distinguish what is a cultural heritage object and what is an archived object. Not all archived objects are cultural heritage. This can be a lot of conditions of time, but this idea is to apply in both of these fields. Then, in this case, we get the participation of 20 countries. We're starting with 14, we're finishing with 20. And we increase the use of the radiation technology for the conservations and consolidations to the member states. This is very important. It's only a line, but you don't have idea how difficult it is to explain this to these people, the restoration and curators of the museums. It's a lot of job, a lot of workshops, a lot of explanation of testing. And we get 77 publications and theses, 2 books, and different meetings as coordinated technical meetings too. Then the idea was to increase the technical projects and, of course, support experts around the world. Maybe the first conclusions of this project was new tangible materials needs to be studied because we don't have a lot of knowledge about what happens when we irradiate different kinds of materials. But very important conclusion of this project was we need protocols and guidelines to preparation for materials, but not to the researchers, not to the people who are working with radiation technology. Maybe to be addressed to the conservators and curators, the museums and the conservation institutions, libraries, universities. Of course, we need the IAEA support for all of these activities. The idea is to go to the wider acceptance of this kind of the technology of radiation processing to preservation, to extending the outreach of the radiation technology. But for this, we need a new CRP. It is the idea with this meeting. Then we call this, for this meeting, like development and implementation, preservation, of course, implementation, talking about to living, to get this information to the final users. The overall objective was the idea is to extend the use of this kind of technology to end users and conservation, but using good practice procedures. This was the main idea. The specific objects of this project is related to study new different materials, or affect the radiation with the properties of these kind of materials when exposed to the radiation, have more interlaboratory collaborations between the countries of different regions like Latin America, Europe, and Asia countries, and establishing appropriate procedures for irradiation to do this in the well way, and develop new materials to try to have like green chemistry now, or green ways to do these materials around the world. What kind of materials we're talking about? Well, archivist disinfection. You can see examples of archivists with fungi attacked in different parts of the world. Insect eradication in the sculptures, instruments, and furnitures, of course. Fungal decontamination of paintings, textiles, and other kind of organic materials. and of course, consolidation and restoration of wood of porous media. Of course, very important is the part of good practice of procedures, and the idea now we are working on that. We are developing a new guideline, procedures, and technical requirements, but of course, as said before, others to the end users, conservators, and curators. This is very important because it's the second publication about this theme around the world. Actually, the second book is talking about this objective. Very important. What are the benefits to the member states? First, we can create a national and regional competence and preservation of this cultural heritage with this technology, because this is an alternative technology. This traditional technology, they use chemical compounds, solvents. The idea is to have another way, another phase of the radiation technology. Don't forget that this technology is not related with uranium. It's not fissile material. It's another, it's gamma radiation. In gamma radiation, don't induce activation of the materials. It's very safe. Second one, participation in international cooperation networks is opportunity is very important to self-exchange, future collaborations, and joint applications. Opportunity to technology transfer to the member states and very innovative fields, creating a basis for future national regional electricity projects, and have a custom-made solution for a special sculpture for one country with special material contaminated using this technology. Our planned activities starting in 2022 and going to 2027. Now we are in the third point. We organized the first meeting in Cairo, Egypt in May 2023. We create some networking collaborations when investigating the factors and the effect of radiation, the functional properties in different materials. And after that, we're going to have a specific forum, maybe during the general conference, organizing the second meeting to research. And the idea is to introduce this probably at almost at the half of the process, extend outreach to the conservators and the curators with different kind of events. The idea, potentially countries can be participating now around the world. Probably the worst problem is South America because we don't have a big participation, but we're trying to do this collaboration in the region. And all of these activities are linked with projects are working now. Projects from Europe, projects from Latin America, or from countries like Egypt, for example, here. Now we are working with 18 countries. They are related, different institutes, special institutes, usually from the government inside. This is the map view. And we don't need to forget what are the benefits of this technology, gamma rays, X-rays, electron beam applications. The idea is use of less chemical waste, no induction of radioactivity when you radiate. It's unique tool for consolidation of porous artifact. Disinfection and the contamination is very fast to do. Environmental friendly processes at any time. Then we did the first meeting. This was in Cairo, Egypt. And after this meeting of all of these conditions, we get the first matrix of collaboration, and we divide in different people's interests, like consolidation, study of side effects of the materials, machines, this means what technology are you using, and studies of microbiology. For example, you can see Brazil is going to have collaborations with Croatia in 4 of these fields, or Croatia is going to have collaborations with France in consolidation and side effects. This is very important, the first network to start out with projects. And now, finally, I want to show you what there may be a summary of the results of the cooperative programs we had in Brazil. Then we participate with last CRP project, and now we are in the one is going. What is the problem in Brazil? Like you know, it's a tropical country, and we have problems with the tangible materials, organic origin, of course, problems with natural disasters. Of course, the problem is raining, water, rivers, and this, of course, become worse with the problem of the insects. Insects like termites, xylophagous insects, and, of course, water plus insects, fungi attack. It is very common in a lot of institutions in Brazil. This, I put here the worst cases, of course, it can be, depends on the conditions. Then, very important thing, we have a special technologies available inside the University of Sao Paulo, IPEN. We have a multipurpose gamma irradiation facility. It's a special machine made in Brazil, of course, and electron beam accelerators, both of them working there. And the idea, you have available this technology, we can offer to the community. And in my opinion, gamma radiation maybe is more suitable technology. And I think the last years we processed around 50,000 cultural heritage with this technology in this equipment. Then, of course, with support with the government and especially for the IAEA. This machine can be used to irradiate small objects like big objects, furniture, even like a scale of a big paintings, 1, 2, 3, 4 meters length. There are examples of the process within IPEN. These are probably more important impact around the community, social community. A big quantity of archives, boxes, containing material contaminated with insects or with fungi. Then the material is put inside of the equipment that is performed the irradiation, and after that is clean, free of the contaminations, to the restorers the restorers can do the traditional work. A big object is not necessary to remove the box of transport. You can irradiate directly. This is very important because of the insurance, the problem of the handling of the very expensive materials. Then even we can put inside. Of course, we ask for people, for companies to manipulate this kind of electric materials inside of the equipment. Very big paintings, modern art is very difficult too because there's a lot of mix of materials. And of course, we work together in collaboration with the national institutes or national governments too. You can see here before the irradiation and after the irradiation. It's very easy to remove the dirty plants or the parts of the fungi inside. This is a special museum is working with us too. Is ethnographic objects. Most of them were irradiated in our facility in IPEN. This cross for the left side is almost 4 meters length. Was contaminated with insects, termites, and now is in exposition. You can visit if someday you will go to Brazil too. Then you can see examples like the people is working with this material. They move, they need to rotate, they need to put inside the machine, they can pull out. But very safely with the transport box. It is not necessary to open the transport box to the radiation make the effect we need. Probably one of the most relevant cases on to the collaboration with CRP is this we performed in 2022 was on the first impregnation and consolidation for the sculpture, wooden sculpture for a government of Sao Paulo. This looks easy, but you have no idea how difficult it is to get the authorization to do this for the museum, for the conservators, and for the restorers. After a lot of administrative process, we start to, this is the first pictures they sent me. I put here, like you said, the dimension, length that people sent from the museum. And we start to do the preliminary characterization. As you see, very destroyed because of the insects attack. It's like almost like a porous media. Then we did first to do something more scientific can be published. Tomography test, no destructive test. Like the human when you're going to the medical doctor, before, after consolidation. We did all of this process using a medical equipment machine. This in collaboration with the University and Hospital of Sao Paulo. After that, X-ray test before and after consolidation. And restorers and conservators were working. We developed a special impregnating reactor to put the resin inside because you need a high pressure. And after that, we perform the radiation. Radiation don't change the temperature, don't change the color, everything is the same thing. And after that, the final stage about the restorative part. And of course, this is not my part, it's for the restorers too. Then the idea, final idea, is that IPEN is working with end users, with national museums, conservation institutes, using extensive disseminations, training workshops with restorers and conservators, developing promotional materials, research and scientific publications are doing well. We provide for them radiation technology, characterization, research and development, basic guidelines of the contamination, or all support with different kind of meetings or different kind of, only addresses to the restorers, of course. There are examples of our collaboration with the National Institute of Conservation, museums, and universities. Thank you very much.
Thank you so much, Pablo. And apart from the tremendous work that you're doing, also highlighting the challenges you have to actually make the recipients of these technologies aware of their benefits. That's it's very interesting to note. So now we're going to move, so we've been from plastic recycling to cultural heritage, and now we have Professor Suresh Pillai, and he's the professor of molecular microbiology and Texas A&M AgriLife faculty fellow at Texas A&M University. He's the director of the National Center for Electron Beam Research, which is focused on harnessing electron beam or E-beam and X-ray technologies for improving the quality of the lives of people all around the world. And his current research is focused on harnessing E-beam technology for a wide variety of applications, including the development of vaccines, food pasteurization, and the remediation of environmental pollutants. And this is what he's going to be talking to us today about. So over to you.
Thank you, Ingrid. Thank you once again for the opportunity to present what we've been doing for a few years now. It's a great honor to be here. So I guess we are in the shadows of the IAEA here at the United Nations. Sustainable Development Goals is a part of the currency of IAEA speak. And part of this is the One Health paradigm. Nothing that we do can be separated from each other. So the environmental health, human health, and animal health, they're so intertwined. So like what Celina mentioned about the IAEA's collaborating, the coordinated research projects, they are completely integrated in all different ways. So if you're trying to solve grand challenges, we have to look at them holistically. So some of the major issues in environmental health are drinking water and wastewater. And this is just the two water matrices. We're not talking about solid waste, municipal solid waste, etc. Just with water, you have major, major challenges, not only because they are in different parts of the world, they have different types of collection systems, but also because the types of contaminants that you have to deal with is very different. Because you have, if you're looking at municipal drinking water, you have to protect the people from pathogens and chemicals. And then the water comes from either groundwater or surface water or a combination of both. So you can just imagine the type of technologies that you have to deploy. And when you talk about domestic wastewater, there are organic pollutants, and that can be divided into chemicals, both man-made natural chemicals as well as microbial pathogens. And then part and parcel of all of this is industrial wastewater, which is another, industrial development all around the world, in fact, for developing pharmaceuticals. They all generate their own wastewater. For example, pesticide residues, pharmaceutical industry wastewater, and the municipal and solid liquid waste. For example, the Danube is considered to be one of the classic studies where they look at pharmaceutical waste and antibiotic residues that show up in the Danube. For example, if you're using surface water for treatment. So any technology that you develop has to deal with all of this. And this is what the coordinated research projects of the IAEA has been focused on for many years. So these are, you can see some of these projects have started back in 1995. The use of irradiation for chemical and microbial decontamination of water and wastewater and sludge. So if you look at the chronology of these projects, they also kind of keep up with the contemporary challenges. So if you look at back in 1995, the big issue was wastewater, sludge, microbial pathogens. But in 2019 to 2024, this last CRP is on emerging chemical pollutants. So you can see, as society has understood what we have to do, the IAEA has kept up with trying to keep up with the science and technology in trying to deal with these issues. Grand challenges, water quality, water quantity. Contrary to a lot of popular understanding, it's not quality that's a big issue. Of course, quality is a big issue, but it's quantity. That's of a major, major issue all around the world. As you can see, no part of the world is immune from water quantity challenges. And all around the world, countries are deploying technologies as for water reuse. And when you hear the word water reuse, there are so many different flavors of water reuse. There's the de facto water reuse, where you take the wastewater that comes from municipal streams, it goes into a wastewater treatment plant, then it goes into discharge into a river, for example, the Danube or any other river, and then that water further downstream is taken for water treatment and then treated. And you can just imagine in the de facto, this is the legacy technology. There are so many technologies that take place in here that one can use ionizing technologies. The other one is the indirect potable reuse, where rather than it going into discharge into the environmental reservoir, it actually goes into another treatment plant. So the wastewater actually goes into a drinking water treatment plant, and then that goes back to the consumer. The more one is the direct potable reuse, which is actually South Africa was one of the leading countries for direct potable reuse, and now it's happening quite extensively in the United States and in many different parts of the world, where the water from the wastewater treatment plant goes into a drinking water plant. So it doesn't go into the environment, it doesn't get wasted into the environment. It actually goes into an advanced wastewater drinking water treatment plant, and that water actually goes directly to the consumer. Obviously, there are some issues and cultural issues about whether somebody wants to drink the water that's coming directly from a wastewater treatment plant. Nevertheless, it is an area that's being used. And one can pick off so many unit processes in these treatment technologies where ionizing technology can play a major role. And that's what many of these CRP projects have been looking at. The other issue which we all talk about with climate change is the eutrophication of lakes and surface water, the toxic green algae. My lab has done a lot of work in showing that microcystin algae can be broken down with electron beam. So as Celina mentioned, at the TRL level, it's at TRL 2 or 3, where we've actually shown it can work. It has not gone into commercial scale because there needs to be a lot of other players who have to come in to deal with this issue of trying to clean up this. So when you talk about CRP projects, you have to keep in mind, it is, like was mentioned, more than the fundamental science is how do you actually deploy it? At the end of the day, it's no point in just filling up glossy journal articles. There's no point in filling up theses and dissertations unless you actually get it to work and make it meaningful to society. So that's where at Texas A&M we're spending a lot of effort on this. So the contemporary view of sewage sludges is that they are significant pools of energy, substrates, and nutrients. We all know because they have carbon, nitrogen, phosphorus. So the original term that we used to call was wastewater treatment plant. That word is taboo right now. Nobody uses wastewater treatment plants. Actually, if you take the train out of London Heathrow, London Victoria, the first sign that you come is sustainable resource recovery facilities. So that's the word that you have to use, and that has a lot of public acceptance as well, because it is no longer a waste. But what it does is that you automatically put a monetary value to it. So sludge becomes an expensive commodity. And that's what the thought process has to be. It's you have to have sustainable resource recovery. And so you have to bring in a lot of different technologies to pull out the energy and to pull out the fertilizer out of it. It is such a travesty to take municipal solid waste coming out of a sludge and just apply it to land and think, oh, well, the plants are being reforested. There's a lot of energy that can be recovered. So how I like to call it is, like the early 90s was the microbial pathogens, textile water decolorization. There were a lot of CRP projects that worked on that, dealing with these, what I call version 1.0 challenges. Then comes in with these organic compounds, which are the more contemporary challenges, which are pesticides, drug residues, opioid residues in water. I mean, believe it or not, these are major challenges. A lot of us, when we finish up with a doctor's pill, where does it go? It goes sometimes into the toilet, right? So they all show up in wastewater, some form of fashion, so you have to come up and figure out a way to deal with it. But the more recent one is the forever chemicals, the PFAS, which is really going to be the biggest challenge I think society is going to face, similar to what happened with PCBs. And in all of these issues, you have to pull out energy, because without pulling out energy, this will be a sink of money. If you pull energy out, then it becomes a profitable proposition. So, oops. So these are PFAS chemicals. How many of you here know about PFAS? PFAS is present in every one of our bloodstreams. 100% of the human population on the earth has PFAS in it. The problem is that it's a developmental toxin. Cancers, a whole bunch of disorders associated with PFAS. And PFAS, this is the reason why, we may think, oh, who created PFAS? Well, it's DuPont and other companies who did it, but the reason is that if you smoke a cigarette and you drop it on your shirt, you don't go up in flames. It's because they are fire retardant. It's a very good fire retardant. PFAS is also used in firefighting foams. So when you have a plane crash or when you have use a firefighting equipment, the chemical in it has a lot of carbon fluorine atoms, which are extremely resistant to breakdown. Even when you buy a McDonald's sandwich, the wrapper, the reason you can hold the wrapper with paper and not burn your hand is because its temperature controls the temperature. And also similarly with carpets, they don't burn up. So this problem, and this is extremely complex now, PFAS exposure to humans and animals. So it is all around us, and these challenges, if you're talking about ionizing technology for environmental applications, you have to deal with this PFAS. If you don't address PFAS, it's really missing the mark. So the challenges is for these environmental landscape is rapidly changing. You have PFAS remediation to driving everything, energy recovery from municipal sludges, waste valorization to put the money onto it, and then now the circular economy, sustainable developmental goals, and water reuse. So what is really interesting and what I've really enjoyed working for the last 2 decades interacting with the IAEA is that IAEA is right and center ahead of a lot of countries in not adopting, it's basically promoting the use of ionizing technology for these applications. So what I'd like to call is version 1.0 is the base technology where gamma and E-beam could be used because the target doses are 3 to 10 kilograms. But once it goes to organic compounds, pesticide breakdown, antibiotics, gamma falls right off the picture because the doses you use are higher than between 5 to 20 kilograms. You cannot deliver 5 to 20 kilograms in a timely manner with gamma radiation. It's going to take weeks, if not. So, and then when you're talking about forever chemicals, you're talking about doses in the greater than 500 kilograms or 1,000 kilograms. And there is no way gamma can fit in. So you also have to see here where alternative technologies, these machine sources, actually have to keep up with the demands that society wants these technologies to play. So the current state of the science for these ionizing technology, it's not a question whether the technology will work. See, back from the 80s, there's been work that's been done in the United States, and you can see, unfortunately, in the 1990s, it stopped in the United States, the work with ionizing technology. There was a full-fledged drinking water treatment plant in Florida that is operating. And everything showed that it could work. But what was stopping the show at that time was the machines that were being used they did not have high-energy machines. Secondly, it was not high-power machines. And thirdly, it was funded by the National Science Foundation, so it was not a sustainable funding process. Since then, China has jumped in and invested quite a bit, and you can see here today it's gone into building a lot of functional things, hospital wastewater, antibiotic fermentation residues, dying wastewater, and landfill leachate treatment plants. So China has taken the lead in using ionizing technology for wastewater and drinking water treatment. So this is a picture, I think it doesn't show up there, maybe it could show, but this is a picture of the Chinese wastewater treatment plant that started in 2017 for decolorizing the textile industrial wastewater. And they've been very, very successful with that. And here it is. So you can see this is how the water flows under the electron beam, like a little waterfall. And of course, you have to see this thin. The water level is thin because the energy that is being used is only about a 3 MeV source. So that's why the water is thin. But you can imagine if you have a larger, higher energy, you can have a larger flow. This is the actual picture of their wastewater treatment plant that has about 7 or 8 dynamotrons that are placed in series for treating dying industry water. There you see on the right is a picture of before the treatment and after the treatment. But when you're using high doses, you cannot deal with this. And this is where Texas A&M, we have spent quite a bit of effort in the last year to figure out how would you deliver 2,000 kilograms to the soil. So when you apply 2,000 kilograms to the soil heats up to 600 degrees C. When you apply 600 degrees C, you have to contain the temperature and pressure. So we're actually working with an engineering company to design these treatment vessels that can deliver, that can withstand 2,000 kilograms, and it'll be put, this is obviously still at lab scale under the electron beam scan horn. So this is where we're doing with PFAS remediation. So one of the things what Celina mentioned, and I think what Pablo and what Jeremiah mentioned was this collaboration of people. So I was approached by the International Water Association to write a feature article on electron beam technology. I could have written the article myself, but I purposely made it an effort to reach out to my Chinese collaborator, Dr. Wong and Dr. Kimilski from Poland, to write this joint article in this International Water Association. We call it Harnessing Electrons to Clean and Power the World. And the reason for this was very specific. How many of you are environmental engineers here? If you have taken an environmental engineering class, oh, you are an environmental engineer?
No, if you're a parent, you're an environmental engineer.
But in environmental engineering, the sad part is, if you look at the table of contents of all the leading textbooks, the last chapter is ultraviolet disinfection, and then it's final exams in the syllabus, right? But there's nothing about ionizing technology. So very many environmental engineers don't even know what ionizing technology is. So our foray into educating the environmental engineering community is an article called Harnessing Electrons and Powering the World. So at Texas A&M, we are a collaborating center. We've been very honored to be in a collaborating center since 2014. Celina mentioned that we may get renewed for the second time, and we are focused on technology for food, health, and environmental applications, promoting the use of e-beam technology. One of the other things that happen is we have a strategic partnership with the National NNSA ORS to accelerate the transition of use of radioactive isotopes to machine sources. And as part and parcel of this is to unleash the private investments in this technology. We feel very confident that we've been able to achieve quite a bit of leeway in this. And the idea is that every country deserves nuclear technologies, but it deserves it to be a safe and secure and sustainable technology. So at A&M, our global vision is we bring together the best and the brightest of science and technologists. We use electron beam technology as nothing more than a 3D printer, if you think, but the applications are very different, the innovations are very different, and our goal is to actually proselytize this technology all around the world so that every country has multiple electron beam facilities because it can fundamentally change how society can improve. So finally, I think that's my last slide, and as part of our activity, a commitment to educating people, we just published a book on ionizing radiation technologies and valorizing waste. I think you had Shima Shayanfar here in one of your other events here, and so we've published some books together in this whole area. And finally, I want to say, remember, e-beam technology can clean, heal, feed, and shape this world and beyond. So always think about electron beam technology as you think about ionizing technologies. Thank you.
Thank you so much for that, Suresh. And again, highlighting the lack of awareness of ionizing radiation and its benefits, but also here showing how e-beam radiation can further expand the scope of applications of radiation. And just before I open the floor for questions from the audience, I want to specifically ask a question about the technologies, seeing that you ended us with the e-beam radiation and this goal of having as multiple e-beam facilities available throughout the world. So from both Jamie and Pablo, if you could just talk a little bit about the technologies you use. I think, Pablo, you were saying you use gamma radiation and the application, why gamma radiation and not e-beam radiation? We also know that in many developing countries there are a lot of challenges with e-beam facilities, e-beam radiation. And we just tell us a bit more. We'll start with Jamie. What radiation techniques or sources do you use and why?
So in the Philippines, we have the gamma radiation facility as well as a mid-energy electron beam facility. And the gamma facility has been very useful commercially for sterilization, decontamination, mostly for food products. And the E-beam is relatively new, but has been very beneficial in materials development. This is because of the unique advantages of electron beam and the fact that this is one of the technologies that can be scalable to industrial processes. Now, unfortunately, at the moment, the Philippines only has one irradiation facility available to the public, which is the one in our institute. But recently, there has been business and private sectors that have interest in this technology. And we are very optimistic that once you open up the private industry towards the use of electron beam, then these technologies can be greatly transferred and the information will be widely better accepted by the people because as Suresh already discussed earlier, there are many benefits to the technology but are relatively unknown to the public and to the private industries. So I think it will create a domino effect so that these technologies can be widely accessible to the public, which is our end users at the end of the day.
Thank you. And so just a follow-up question. Do you think there is a difference in the acceptance of people and the public in general and industry if it is an E-beam facility versus a gamma radiation facility, or is it just broadly irradiation is difficult to accept?
Broadly, yes, irradiation, there's still a lot of misconception. When I talk in public about it, their first question always is, are the materials we are irradiating, are they radioactive? Do they become radioactive? So there is still that stigma with radiation technology. But more recently, because of the inclusion of nuclear technology in our secondary school systems, in education, as well as the information dissemination done by the Institute on a national level, we are slowly destigmatizing the technology. And one of the things is, as for the gamma versus E-beam, E-beam is generally more acceptable towards private industries because there is less regulations in terms of radioactive materials and their implications. And also, again, as Suresh said, gamma facilities are very slow in terms of delivering the required doses for industry. So for that, generally, if you want to industrialize the process, usually we go for E-beam.
Thank you. Pablo, what is Brazil's experience?
In my opinion, well, we have both technologies, but the problem in my case is available. It's possible to irradiate, but the energy with my E-beam facilities is not enough to penetrate this kind of material by irradiating with cultural heritage.
Because it's a deeper...
Exactly. Like Suresh said, it depends on the depth and the energy. This is very important. But for their side, gamma is very flexible to do that. And I have a lot of time to do that. I don't need to do like a river.
It's not industrialized.
Then, in my case, the precision is more important, like the speed. Then we need to do this perform very, not fast.
No, but
slowly taking account that the dosimetry, the distribution of the dose, because we don't need to have a part of the piece with low dose and with high dose, because the effect can be very different.
Yeah.
And then we prefer to do with gamma at the beginning. But we're doing some research with electron beam irradiating cinematographic films.
Oh, okay.
Yes, I didn't present this because we don't have to do that, but to increase cross-linking inside. Is a problem with the name is called vinegar syndrome, and the reaction start to go out like acetic acid again, and it smells very bad. But a very important films, and we do irradiation with electron beam because it was the best way to do, and we create cross-linking and we stop this reaction. Oh. And after that, we take into make digitalization of these movies is very important to keep to the society. But in the first instance, it's possible to do with both technology. But the other side, we have it's not problem for my country to buy cobalt-60. because we are neighborhood from Argentina and we have a special agreement with governments. Then this is another issue related to the cost and
because many countries struggle to gain access to cobalt-60 because
exactly.
the transport issues, etc.
Exactly. It's not a regulation problem. It's very different. And like they said, electronic machines you can turn off. It's radioactive. Turn off. It's not more radioactive.
Yeah, and so there's also the security issue around radioactive sources and the use of radioactive sources. You have to have everything in place to ensure that they can't be stolen and they can't they can't be left behind, and they have to be taken care of throughout their entire life cycle, right?
Exactly.
But their application, it depends on what you are trying to what do you want to treat and what your end goal is and what the material is. That then defines kind of what the radioactive sources or EBIM.
Exactly. Even the last research, we're working with the dose rate. This is related to the speed. In some organic materials, tangible materials, you can destroy with high dose.
With high doses. Yeah.
Even with the dose you need. Then this is a special research field, but however, we work with cultural heritage between 6 and 5 kilograms per hour.
Okay.
We are working with electron beam, you can reach 1,000 or some 6,600. Then you can create, like Jeremiah said, like you can create scissoring, and you don't care with the infection or the insect because you're destroying the material.
Yeah.
And the first signal of the change of the material is the color. It's very evident, yellowing, like old aging materials.
Yeah. Okay, that's very interesting. Thank you.
I think, for example, cultural heritage is a classic example where we cannot get rid of cobalt-60. The reason is when you have large triptychs from monasteries or churches, you cannot get that under an electron beam facility. So he does, like you saw, large, complete statues. And for that, you do need bulk irradiation where cobalt-60 is the only one solution there. But to your question about countries adopting the technology, I think it's a matter of time when the technology becomes widespread. Right now in China, there's over 700, I think close to 900 e-beam facilities doing a variety of applications. Even though China is one of the largest producers of cobalt-60, they're actually going down in volume compared to electron beam. The other challenge, like what you were mentioning, is about power sources. The country of the Dominican Republic has an electron beam facility that's completely running on an electrical generator set, because they have the value of that business is so high that they can afford to have a generator set running it. So it is going to be, creative minds have to come into play as how do you build sustainable facilities. It's not, you cannot parachute a technology into a country, whether it's the United States or in any other part of the world, you just cannot bring it in like that.
And that's where the CRPs are actually so useful as well, right?
Yeah, and thanks to the CRPs, we have hosted a number of at the IAEA, we have hosted a number of visitors at our facility. Even though we could have hosted them longer, but at least them seeing a functioning facility gives them confidence to do it. And I think that's how Pakistan's adoption of e-beam technology in in a very volatile part of the world, they didn't obviously want to go with cobalt-60. They put in electron beam, and it's being very feasible, sustainable now.
Okay, great. So let me open it up for questions. Yes.
I have a question.
Can you introduce to say on? Oh, there we go. Yeah.
My name is Gertrude.
Is it
Hello?
on?
Does it work?
Oh, yeah, okay.
Okay, I hope you hear me. My name is Gertrude Oelmark, and I have a question to Professor Pablo Vasquez and to Professor Jeremiah Barba concerning the gamma radiation technology. Also what I learned long time in school, that gamma radiation is the most harmful to human beings because you cannot shield yourself against it. I mean, with alpha, a paper between you and it is enough, so you don't get it. And with beta, a little bit more you need, but gamma radiation, basically goes through everything. So my question is, if you work with this technology, how do you protect the humans who work with it?
Okay, thank you very much for the questions. Of course, we don't have a lot of time to do the explanation how is working these facilities, one of these facilities, but the sources or the place when it's performed the irradiation is closed around a shielding, a biological shielding done with high-density materials like concrete, like lead, or another, like in some cases you can have walls of 2-3 meters length. The idea is all of these practices performed inside.
With machines?
With machines, of course. You have a special door to open it or a special system to transport the material inside of these bunkers. When the material is inside, only the material gets the radiation. The operators are outside in a special control room. Nobody gets radiation. Of course, maybe 2-3 minutes for a human is more than.
And this is the same for e-beams, because we're talking about safety here, not the security, and there are very strict guidelines, and the IAEA and the member states work together to develop these guidelines and requirements for when you use radiation. Laura.
Thank you very much, Laura Rockwood, Senior Fellow here at VCDNP. I was astounded at some of these applications, just astounded. And I bet you outside of the people with whom you work, and now the people in this room, it's a darn small community that know about this. Has the agency considered a promotional program to inform the general public about these things? I remember years ago when I was at the IAEA, we used to have meetings with journalists to inform them about what's going on. BBC, CNN, these big news organizations that are looking for newsworthy things like this. And it doesn't have to mean you're pro-nuclear energy. There are so many other applications besides energy that are so important. And this whole idea of these forever chemicals, this is the catchword of the day. Get out there and advertise it.
Celina.
Yeah, I fully agree on that. Absolutely agree. This is our mission. Actually, there is one department that depends directly from the DG office that is trying to find out which are the best strategies to advertise what we are doing. Of course, they are very strong on social media. If you go into the social media, there are, all the time they are advertising, they are tweeting, or there are, Instagram. So all social media are being, full of this kind of application. Nevertheless, what you have said is right. No, we have to go forward and go through still the conventional media. No, BBC or all this kind of. For example, once a year during the general conference, also we have what is called the scientific forum that has been mentioned also by Pablo, that in 2024 we are planning to have a scientific forum on the use of nuclear techniques for the cultural heritage, because it's not just the preservation and consolidation. There are some other colleagues that are working on the characterization of this, on the dating of this kind of cultural heritage. So there are different techniques that can be used to support the restorator, the museum, and all on these techniques. So in 2024, and this scientific forum, for example, is being done with one journalist that is from the BBC, and she's the moderator of this scientific forum. And it happens every year we have this kind of scientific forum. Of course, we have to split because I love our application, of course, but we have to share the law with other colleagues in nuclear energy, in nuclear safety. So depending on the year, which is the purpose of this scientific forum. But this is just one example that we are doing. And again, I agree with you. Some other program that we are doing is what Jamie has mentioned. For example, in the regions, there are some technical cooperation programs that are reaching the secondary school. So the student at the secondary school and also the teachers, that is very important, is the training the trainers are now more aware of this. And for example, there are some tournaments such as video preparation of some particular purposes. So, for example, last year we have on this New Tech Plastic initiative that she has very well presented. So all the secondary school from all the Asia-Pacific region prepared some video, animation, and it was amazing, the work that they have done. So the teachers were aware, the students were more aware, and they were aware those that were relevant. All of them were amazing. But this is some different program and strategy that the IAEA is using, no? But there is still a lot of room to do. Yes, but we are yeah.
But I think here as well is the role of the diplomats and all of us in this room, right, and online. And the reason we also have these panels is, when I was a diplomat here, I never had even I had the smallest idea of what the scope was, and I'm still learning every day, and it's unbelievable. But I think this is also the challenge that we face in all our countries, be they developing or developed countries. There's a lack of understanding of these benefits, of their applications, and how much they can actually contribute. And I mean, here we have Norton Titus from Namibia, who has on many occasions also very, very poignantly expressed what a challenge it is in countries where these applications could make a world of difference in ensuring that there is that you get fruit and vegetables to the market and to the plate and to the fork, and without these, if they had these technologies, it would actually improve food security. And I think all of us have this experience in our countries. Sorry. You wanted to say something?
No, I just back to the comment there. It has to be relentless communication, and it is also talking to the the media influencers. I mean, we checked. Beyonce charges $250,000 for one tweet. For Kanye Z charges almost the same amount. So we cannot touch those type of media influencers, but we have to come up with different approaches. And so yeah. It is. Everybody needs to continue to communicate.
I do it for free.
Yes.
Exactly. Right.
Yes.
Okay. Good afternoon. My name is Milan Ilic. I'm since 30 years. I'm based in Vienna and accredited as a foreign journalist. So, I'm as a journalist, I'm not afraid to ask silly questions. So probably it is a silly question. But I have to ask you, when I see the scope of applications, and in some or in several very important fields, could you imagine that this technology or the development or in the, foreseeable future can or could help us in neutralizing maybe the glasshouse gas? Gases like carbon dioxide, methane, and some other.
Yes.
Not a stupid question at all.
Not at all. So that you're talking about the decarbonization.
Yeah.
Decarbonization, if you actually look, we've done analysis that heating with electron beam is cheaper than heating with another method because it's directed energy heating. So when you heat something, you're not heating up the vessel, you're only heating up the product. The challenge is the technology has not kept up pace to offer the industry those types of heating elements in electron beam. Yes, so basically, absolutely, the answer is yes, decarbonization electron beam has a major role in this area. Maybe your IAEA is doing some work in that area too, right?
Actually, well, next year we are planning to have a new CRP on the volatile organic compounds and the gradation of this kind of. So it's in line with this kind of decarbonization. Yes, actually, this is one of the gaps that we are looking for. We are just to prepare the right CRP direction. We are having, for example, this year one consultant meeting inviting experts to create the draft of this new CRP. So we are working on that direction now, actually, yeah.
So just to add to this point, you know, when you buy an airline ticket, they say you can pay an extra $50 to reduce the carbon footprint. But what they don't tell you is that the pretzel bag that they give you, that pretzel, frying that pretzel uses more CO2 and release more CO2 than you flying. Okay, so and
I don't eat pretzels,
and the heating of the pretzel, the frying, the baking industry, these are all areas that this technology potentially could come in and disrupt.
Susan?
Susan Cohen. I'm a technical editor for actually most of the organizations represented here, but mainly I have been for the IAEA for about 30 years. I have a question to Professor Jamie and a suggestion for everybody. My question to you is the process you described, I could imagine would be interesting to all the countries in the region. Have you held regional workshops on it?
So yes, IAEA has actually arranged for regional workshops, usually by region, so Asia, Pacific, Latin America, and Europe. So there have been several workshops as well as training courses to disseminate this information first to our fellow scientists, which are directly involved in the plastic recycling scheme, and eventually we hope to disseminate it further to stakeholders, especially for us in our country, to the national stakeholders, the ones who are actually going to benefit and use this technology to widen the scope of the outcomes that can be gotten from these projects.
Thank you. And my recommendation is the following. As a basic reading before people get onto your book on technology, for example, an excellent booklet has been put out by UNSCIA, which is a tiny organization in the VIC. I don't think anybody from UNSCIA is here because there are only 5 people in the secretariat as opposed to 2,000 at the agency. Yes, UNSCIA stands for United Nations Scientific Committee on the Effects of Atomic Radiation. And what they do is radiation measurement. They work closely with the IAEA and with WHO and other organizations. And they've put out an educational booklet aimed at the general public who have some scientific knowledge, but let's say high school level. And it's called Radiation Risks and Benefits. It's free. It's online on the UNSCIA website. I don't get a commission for this, by the way. It's also available in hard copy. It's already in many, many school and college libraries. And it's available, I think, now in 15 languages and still growing. So I can thoroughly recommend it. It answers a lot of questions that people, in fact, the question you asked today, about what radiation is, where does it come from, what are the sources, what about accidents that have happened, above all the big ones, 3 Mile Island, Chernobyl, and Fukushima? What about radiation that you might get when you fly in an aeroplane? It is really an excellent 42-page booklet in understandable language.
Thank you, Susan. Thank you.
Suggestion as pre-reading for your excellent booklet, your excellent books. And also, I just want to say thank you for very educational and eye-opening presentations on these nuclear applications. I learned a lot.
Thank you. Any other questions from the public? From you here?
May I?
Yes, absolutely. You can just use the microphone. Yeah.
Just to add to what Jamie has said, I agree with you, Susan, that, for example, IAEA has found that this topic on the upcycling of plastic waste is an issue, global issue. That's why there is an initiative. IAEA has 3 big initiatives, flagship initiative it is called. One is New Tech Plastic Initiative, and it is working with all the 4 regions around the world to deploy the technology, to develop and deploy the technology. That's why Asia Pacific is one of them, then Latin America, Europe, and Africa. So all together we will find out the different strategy. There is one 4-stage approach that we are working together in all the regions, but of course also respecting the times and the needs for each region. So this is a big flagship initiative that we are working with all, delivering all the knowledge, but also supporting at the individual case by case. So this is something bigger than just one regional workshop. So this is such a big strategy we're working with. This is just to let you know.
Yes, Norton.
Yeah.
She's trying.
It's good exercise.
Thank you. I'm Norton. I'm currently at the Permanent Mission of Namibia. So, yeah, I grew up under a, what is it, sustainable
Development goals.
recovery
Facility.
resource facility. So I don't know any other water from any other place. And it happens to be Windhoek, I think, the first country in the world that did reclamation.
Yes.
So yeah, proof of the concept that it works, even on people. But I just have one comment to make, and it ties in with what Suresh says. The promotion of this has to be relentless. There is such, it's almost like blowing against the wind, in which people are concerned that what I'm eating is radioactive and I don't want to have that. Whereas, 1 week extra with more life, or 2 weeks more lifespan in a tomato allows the grower to get it to market, allows the market to sell it, and allows the user to use it. Rather than 3 days where the product is not what the user wants. So, there are technologies, for example, for my country where they do poaching, a lot of rhino poaching. I mean, there are projects where they try to inject some radioactive material in rhino horns so that you can detect it, and thereby preserve, it's not bad for the rhino, but in some way preserve the rhino horn, or detect it if it gets smuggled somewhere. So these are the massive applications that there are. But I want to ask, like, for example, with Suresh in needs application, I somehow feel that the private sector needs to see that there is an economic benefit for it, and in some way you sell a whole package, like I've seen the IAEA do with Rays of Hope, trying to sell a whole package. It's almost like selling a Tesla, but they've already put the infrastructure there for you to fast charge, because they know what the issue is. One of the biggest issues is obviously the supply of electricity to run these facilities. And the genset, can be run by a private entity once they make a profit.
Yeah.
Coming from government, we take our time, because it's important to take our time. Because I don't want to make a decision, with public funds. But the private sector will move this thing forward fast. What would be your suggestions in terms of making this more attractive?
Norton, that's a very... Oh, sorry. Oh, sorry. I've been snatched. Norton, you're absolutely right. So at Texas A&M, and in our approach and a partnership with the U.S. government, our approach is to get the private industry involved. And we are looking at non-traditional stakeholders in private industry. Who we are approaching right now are the big builders of resorts, hotels, and other places. Like if you look at every country in Africa, there's a data center, okay? One data center uses more electricity and more water than a traditional 10 MeV electron beam facility. So that equation, that if you can make money, then these resources are non-issue. Now who we have found from the hotel developers is each of those hotels, whether it's in Namibia or in Botswana, they are $70, $80 million programs. These are like $10, $20 million. So it's peanuts. But once they see the dollars, the return on investment, for them, they're all wanting to get in. In fact, in the US right now, one of the biggest builders of the Hilton hotel chain is very much interested in getting into this business of e-beam businesses. But for them, it is primarily a pure commercial venture. And that's how this technology has to be. It should not become, oh my God, it's such a great technology that only sacred hands can touch it. No, it should become very commonplace. So our goal is basically that, working with non-traditional stakeholders to invest.
And how is this translated in your countries? You've talked a bit, Jamie, about that. And is it been difficult to get private sector involved?
So again, going back to the stigma against nuclear technology, so because of the recent shift in interest in nuclear technology, more and more private sectors have been talking to us with regards to the materials that we are able to produce. And this is because they see firsthand the benefits, not just the technical benefits, but the economic benefits. So one of the, say, flagship products from PNRI is the plant food supplement from the radiation degradation of seaweed. So you take something as common as seaweed, you subject it in radiation, and you have something that can be sprayed onto plants and crop yield increases. So, of course, as the normal public is like, what are you spraying on our plants? Mm-hmm. But there is evidence across all regions most regions in the Philippines that there is crop yield in rice, in peanuts, in corn, in bananas. And this type of situations are now opening the eyes of the private industry in accepting this technology more. So we hope with greater promotions, as well as in extending our applications to very diverse fields like environment protection, in plastic recycling, in materials development for specialized functions, we hope to engage them further so that this becomes a mainstream technology and not just a special novel technology somewhere.
And
Yeah,
Pablo?
I want to share some experience talking about this field of economics, but maybe the more important in my experience was the relation we create with the department of my institution, the journalists, because this was and is a problem. We publish scientific articles, or we did some talks. We use special terminology that is like an alien language for the other. But we need a special team to translate it and to put this to the society. And this action we started in 2012, and we have a lot of good results. After 5 or 6 years, we have a lot. No, the schedule of the facility was totally full. It was not possible to talking about only cultural heritage.
Only cultural heritage.
Only heritage.
Wow.
But this you need to be done every day. You cannot left behind because it is a special activity. I'm not talking about like a country. I'm talking about the nuclear institution university. It is more part, and after that, of course, you can be together. And this team create with us a special relation with the TV program. Mm-hmm. They do a lot of interviews, and we did some advertising about that. Not using scientific terms, but showing to the community what we are doing in the name nuclear institution work. And the other thing I want to comment is like you need to see the nuclear technology like a step. Suresh showed these water plants in China or in Korea, but this is not only a step. The traditional processes are around: chemical, biological, physical. Radiation technology is one piece put inside of the system. And we need to, this not solve all problems.
It's not solve all problems, but in combination.
In combination
with
a better solution to the weather and environmental solution.
Exactly, like nuclear power, for instance, has the combination. But I mean, you also wrote this paper on emergency applications of radiation processing for decontamination of personal protective equipment for COVID. Now, wasn't this also an opportunity to have people better understand the benefits of this technology? Because we saw that with the IAEA during COVID, when they were able to really reimagine themselves or have the public see them differently, and not just as a nuclear watchdog, but actually as contributing to life-saving applications. So is this something, did you find that during COVID and doing this, that also added to better understanding of the benefits of this technology?
Yes, this was actually a special situation in Sao Paulo, Brazil. This is a big city, 23 million people. And when it started the pandemic, it was a terrible thing I remember in my life. Then the problem was the poor communities neighborhoods, they didn't have masks.
No.
And they start to do this with textiles. But
Yeah.
textiles with not conditions, sterile conditions, sterile. And they ask help for free, of course, to try to make the irradiation of these materials. But the problem was we have no idea what was the situation, what was the COVID virus, the resistance, and how many kilograms you need to apply, the dose. Then we start at the beginning to try to understand what happens with the virus and the behavior with the radiation. And then we get some dose, and we start to apply 1 million masks, maybe we radiate for these communities, poor communities, because it was the situation was of emergency.
Mm-hmm.
But after that, the company, the private company, they use not our service, private service, because in Brazil is only two kind of irradiation facilities: the government and an American international company. Then they start to use this service, but we start to do the research. This was
and so that's that collaboration again.
Yes,
yeah.
of course, because when they are in our schedule, we are full. We're not possible to process a big quantity of cubic meters or tons. The only solution, they need to pay a little more or go to the private company. But for them was a good business, I think so.
Exactly. So this is also the question of that you were mentioning with the CRP, and you have the research and development, and the IAEA facilitates this bringing together of big minds in the world, the challenges that we face together, and then having this transferred to countries and private industry also then benefiting from that. But how do you fund that work on the CRPs? Where does the money come from?
So the money can come from the, well, of course, regular budget. That is what we are, of course, when we are planning to make it possible, the CRP, we have to plan from the beginning, the budget that we are going to require, especially the number of candidates. But fortunately, we have received support from different donor country and organizations to make it possible. So that's another opportunity that we had found during the last time, especially when we are advertising properly the kind of achievement that we can have. So that's why we have been involved with different permanent missions from different countries, and they found it that there are many CRP that are in the direction that they are interested in to support. So that's why, for example, in this New Tech Plastic Initiative, we have received funds from different countries that are fully supporting 2 CRP now. So, and from different countries.
And that's extra budgetary money,
and it's
basically.
Extra budgetary funds that allow us to, well, increase the number of participants, the countries that are participating, and maybe the funds that can be delivered to them. So this is very, very useful. And this is, well, when I always say that I am not a scientist anymore, I'm more a businesswoman now, because I have to do some business in order to advertise what we are doing. So I'm learning also, because I came, as I always say, I rat a lab, no? I came from the lab. So I have to know how to better advertise what we are doing, and which is the main outcome that we can have through this CRP implementation. So this is part of our, yes, we are there coming from different member states in the IAEA and learning the process and finding the best strategy that we can use to implement this, getting the funds, supporting member states, and using all this in the same way, in the best way that we can find.
Thank you so much, and we've come to the end of the panel discussion. I'll just give everyone a moment to say some concluding remarks, and just to thank you again, because for me, I think this is continually an eye-opening experience. I'm amazed that we are working with an organization like the IAEA, with the member states, what they are doing, how we are on a daily basis finding solutions together to address some of the biggest challenges we have with nuclear technology. And we really hope that we can contribute to spreading the word and to making your work more visible and to getting more support, more broader support as well from our member states, from private philanthropic organizations, from development organizations, so that we can continue to do this. Let's start with you.
So just as a final thing, we've seen from all the presentations the benefits, the peaceful uses of nuclear technology, from water treatment, environmental protection, health applications, cultural heritage, preservation. And the important thing here is to keep an open mind, because this is just science, and we can deliver evidence-based facts that nuclear technology does help in these situations. And keeping an open mind will enable the general public, everyone, to benefit from this technology. And hopefully in the Philippines, we can also pioneer our applications for our national agendas, as well as from the region in Asia Pacific and all around the world. So thank you very much again for this opportunity.
I think that the job the official people is doing in IAEA is very important. Don't forget the problems with Fukushima and the problems with now Chernobyl again. And you need to think that this is not exactly nuclear related with uranium. This is radiation technology. Radiation technology is not activation, not create activation. It can turn off very quickly, like Suresh said. Then we need to maintain this in mind. And I think IAEA is doing the best way now, showing the other phase of the nuclear applications, medical, environmental, cultural heritage. Thank you very much for the invitation.
So, yeah, thank you very much. And my point would be that all the technology that we have presented today here are globally approved by all member states. It's not something that we are creating now. It has been approved for more than 70 years. So we are just adjusting application into emerging new applications. So taking advantage of what has been done in the past with this technology. Of course, the technology is evolving, but the kind of technology has been already approved. So the idea or our proposal from IAEA is to take advantage of this technology into innovative applications, such as we had seen during this presentation, in the upcycling of plastic, convert plastic waste into valuable product from cultural heritage. There are limited conventional techniques that can be being used for preserving this kind of cultural heritage in the sustainable resources. So I got the point. So actually, I was thinking also in the biomass. It's some kind of biomass that we can convert into such a valuable product. So, but again, we are adjusting the technology to this application. So this innovative application, this opportunity that we have found. But the technology has been already approved. It is approved, and it's globally approved by most of the member states around the world.
Thank you once again for VCDNP for this opportunity to present. But I actually want to say, among all the United Nations organizations, I don't think there's any other organization like the IAEA that does these coordinated research projects that's been going on for so many years. We sleep better at night knowing that Zika virus is being protected because of sterile insect technology with mosquitoes. We don't worry about screwworms because that is being by sterile insect technology. So these technologies are like the policeman or the military that's protecting us day in and day out. We sleep better at night because these technologies are already being used. But what I want to be optimistic and say is that what you're seeing today, or what you've been hearing, I think is just the beginning of this revolution of this electron. We are all built with electrons. There's nothing more organic than an electron. So when you start harnessing these electrons, you can imagine that you can create magic. And I think if you see what Celina in the presentation said about these biomaterials, what is happening is when you're starting to tweak around these electrons, you're starting to see some very unique molecular interactions that bring up some very high value applications. So extremely optimistic into the future about where this technology will lead us.
Thank you so much, and thank you to everyone who, again, has braved the weather, and we are going to give you wine and food so that you can be better prepared for your trip home. And everyone who has signed in online, thank you for participating, and we look forward to seeing you at our next panel. Thank you.